Hi, my name is Nathan TeBlunthuis, and I'm excited to be here at Opensym to present my research on measuring Wikipedia article quality in one dimension by extending ORES with ordinal regression. I am a PhD candidate at the University of Washington, and I'm about to graduate and start a postdoc at Northwestern, and I am looking for a full-time job for after that. Assessing the quality of articles is an important practice on Wikipedia. Wiki projects regularly conduct quality assessments to monitor the quality of the articles in their purview. These quality measures are also important motivators for Wikipedians, as raising an article to good or featured status is a real achievement. Article quality ratings in English Wikipedia have been widely used also in research to investigate topics ranging from donations, political polarization, or tracking knowledge gaps. Now, the article quality assessment data generated by wiki projects does have some important limitations that have motivated sort of model-based techniques for measuring quality. The first of these is that these assessments happen at irregular points in time, and articles do change in between these assessments. Machine learning models, like the ORES quality model, can predict the quality assessment an article would receive if it were newly assessed. This allows us to sort of extend the range of quality measurements beyond the range of these direct observations. The second issue is that articles are labeled on a discrete ordinal scale with levels stub, start, C, B, good, and featured. And this makes a lot of sense when it comes to conducting assessments, that it's kind of inconvenient for statistical analysis. A discrete scale can't measure levels of quality in between its levels. If I improve a C article, but not all the way up to B class, that improvement just isn't captured by these article quality assessments. And my project provides an improved way of dealing with this second issue. To understand my method, it helps a little bit to think about how the ORES quality model works on the inside. This diagram sort of shows this at a high level. The idea is that you have a set of boosted decision trees, each of which output a score. These scores are passed through a softmax function to convert them into a normalized probability distribution where all these probabilities sum to 1. So essentially you get a probability that your article is a featured article, a good article, a B article, and so on. So a natural way to convert these probabilities into a single-valued measure of quality is to take a weighted sum of them. And this is an approach that was first introduced by Halfacre and has been adopted by other researchers, including by Arezia et al. And the idea is that you handpick sort of these weights, 0, 1, 2, 3, 4, 5, and then you take a sum product of the weights and the scores to get a continuous measure of quality. So that's 0 times the probability that your article is a stub, plus 1 times the probability that it's a start, plus 2 times the probability that it's C, and so on. Now, doing this kind of depends on this important assumption. In the words of Halfacre, the ordinal quality scale developed by Wikipedia editors is roughly cardinal and evenly spaced. But I think there are some reasons to question this assumption. One of them is that the levels of effort that go into different levels of quality seem kind of uneven, right? So writing a featured article can take 3 to 6 months of full-time work, in the words of Stuart Yeats. Are we to assume that the difference between a good article and a featured article is the same as that between a stub and a star class article? How would we even answer a question like that? So my method works by using a piece of information about the quality levels that the ORES quality model does not. This is the fact that these quality levels are ordered. If you stare at this equation, which is what the ORES quality model is minimizing, the multinomial log loss, you'll observe that there's nothing in here at all about the relationship between the different quality levels. All correct classifications are rewarded the same, and all misclassifications are penalized the same. It penalizes misclassification of a B-class article as a stub the same as if that B-class article was predicted to be a good article. Ordinal regression provides a way to simultaneously estimate these coefficients, which we'll use to combine the ORES probabilities into a single-valued measure of quality, and uses the fact that the quality levels have an order to them to penalize misclassifications that are off by a greater degree more than misclassifications that are off by only one level. And we'll estimate these alpha k parameters, which tell us the distance between the thresholds. Now, under the hood, because these different probabilities are collinear, I'm doing a little bit of linear algebra to deal with that underneath the hood, but conceptually, this accurately shows the idea. My method deals with one more important limitation of the ORES quality models. This is that they are fit on a balanced data set. Now, this means that each quality class is an equal representation in ORES's training data. This is a reasonable and common choice in a machine learning perspective, because it can lead to like more accurate predictions across all the quality classes. But it does lead to miscalibration in the probabilities, which in turn can lead to decreased accuracy. So during this process, I'm also recalibrating these ordinal regression models to units of analysis, which will be more useful to researchers like articles or revisions. No matter which unit of analysis we choose, the article quality classes are not evenly spaced. Each of these models, the article model, the revision model, and the quality class model, all find that the distance between sort of a start class and a C class article is relatively small compared to other classes. But exactly how these quality levels are distant from each other kind of depends on the unit of analysis. From the perspective of quality classes, the quality class unit of analysis, you'll find that there are relatively evenly spaced. They are relatively evenly spaced, but from the perspective of dataset representative articles or revisions, they're much less evenly spaced. Next, I find that using a model calibrated to the appropriate unit of analysis provides improved accuracy. This table just shows the accuracy numbers for each of the 3 models that I fit, plus ORES for the quality class dataset, the revision dataset, and the article dataset. And it turns out that for the revision and article datasets, the ordinal quality models are considerably more accurate than ORES is. That being said, these quality scores are all highly correlated. The different ordinal model quality scores are extremely tightly correlated, and they're even highly correlated with the evenly spaced assumption. Now, if you look at these charts that show the correlation between the evenly spaced scores and the ordinal scores, you'll see that there's some disagreement, especially in the middle range of quality. In conclusion, I encourage you to use appropriately calibrated quality scores from an ordinal model if you need a one-dimensional measure of quality. I'm releasing the code and datasets for this project, and I'm also working on publishing a more user-friendly version of the code to support other researchers in using this technique. Also, I encourage you not to assume that quality levels are evenly spaced, but rather try to use models to make inferences about quality levels. Finally, I think that it's important direction for future research to build machine learning classifiers that are appropriate for ordinal data, so that we don't need this sort of complicated 2-step process where you take the OR scores and then we also have to fit ordinal model. Instead, we could just recalibrate scores to our unit of analysis. Thank you. My email is nathante@uw.edu. There's other contact information from me on this slide. I look forward to your questions and discussion.